Okay, now we want to look at the column space. There are 4 column vectors in this matrix. 1, 1, -1, 1, 2, -1, 1, 1, 1, and 1, 2, 1. Do they form a basis? And I don't say here a basis of what, and I actually forget whether it was a basis of R3 or a basis of the column space. So we can answer it either way. Okay, so let's just answer the question of whether they form a basis of R3. Now, we had a little trouble in class getting people to tell me what a basis was, and at this stage I would hope people, with a test coming up very imminently, I would hope that people would have a little better command of what a basis is, but the class pulled it together pretty well for the first test. I assume that the same will happen. But anyhow, basis is a linearly independent spanning set, a linear independent set that spans whatever space you want to look at. Now there's more formal definition, and you want to be sure you know that definition, but I'm assuming that you do or you will. So that's really what it comes down to, a linearly independent set that spans whatever it is you're looking at. So we want to know if the column space, the set of 4 column vectors, is a linearly independent set that spans R3. Well, or let's say a linearly independent set that spans the column space. So let's lock that in. Let's say that's a basis of the column space. Okay, because we can't say that the columns span R3. We can't say that the columns span the column space, because that's exactly what the column space is. It's the span of the columns. Okay, now, do these form a linearly independent set? Okay, well, the dimension of R3 is 3. Okay, for example, these 3 vectors span R3. We could write them as columns if you, well, I've got them as semicolons, so they are columns. But this is a linearly independent set that spans R3. Any basis of a space, all bases of a space, every basis of a space has the same number of vectors. Okay? And the number of vectors in any linearly independent spanning set in any basis is the same as in any of the other, and that number is the dimension of the space. And no linearly independent set can have more vectors than a basis. Now that's something you know, something you would have proved, something we've talked about already. So no linearly independent set can have more vectors than the basis. So the number of linearly independent vectors in any basis of anything can't be bigger than the dimension of the space it's in. So we can't have 4 linearly independent vectors in R3. So these 4 column vectors can't possibly be linearly independent. And those are properties that you really want to be very comfortable with when you take the test. Okay? So the answer is, well, yeah, certainly the column vectors span the column space, but they don't form a basis, because the dimension of the column space can't be bigger than the dimension of the space R3 where they all live. Okay? All the column vectors are in R3. So we can't possibly have a linearly independent set of 4 vectors in R3. The column vectors are in R3, so there are 4 of them. They can't be linearly independent. Okay, that's very much an airtight argument. So my now question is, how do we get a basis of the column space? Well, the reduced matrix has 3 columns corresponding to rows with leading ones. I've circled them here. Okay, this row has a leading 1, this row has a leading 1, this row has a leading 1. A leading 1, in case you've forgotten, is just a 1 that has nothing but zeros in front of it. Okay? Now, the first, second, and third rows here have leading 1s. That means that the first, second, and third columns that I've indicated by arrows in the same color will be a basis for the column space. So right there is a basis for your column space. So that's all we're saying over here. And then we have another thing about the dimension of the row space and the dimension of the null space. Also, I didn't write it on the board here, but the dimension of the row space equals the dimension of the column space. Okay, and the dimension of the row space is what? Well, all these vectors are independent. Okay, none of these vectors can be obtained as a sum of any of the other two. This first row can't be obtained as a sum of the other two because the other two have zeros here, and then we can't add multiples of these zeros to get this one. This one has a zero above it and below it. We can't add multiples of the first and third row to get the second row because there are no multiples of 0 and 0 that will add up to 1. And similarly, we'd say the same thing for the 1 here. It can't be a sum of multiples of these zeros, so we can't add the first two rows to get the third. So the three rows are linearly independent. And we're used to seeing that in many ways. So we have three linearly independent rows. That means we're going to have three linearly independent columns. Now that leaves, well, that tells us that the row space of R4 has dimension 3. So this circle represents R4. This yellow boundary includes within it everything in the row space. That's the whole row space. Now this is just a schematic diagram. Things don't look like that, you know. But the diagram gives us the picture. The column space has dimension 3. There are three linearly independent vectors. So the column space does form a basis of R3. So the row space maps onto the column space in R3. Okay, and column space over here is equal to R3. What's going to happen to everything else in R4? What happens to everything else in R4 is it maps to the 0 vector. Okay, so everything that maps to the 0 vector can be proven to be a subspace. So what we've done is we've divided R4 into two subspaces. One subspace with a dimension 3, that's the row space. Another space with, well, it has to have dimension 1. Okay, because R4 has dimension 3, the row space has, did I say that right? R4 has dimension 4, the row space has dimension 3, everything else has to have dimension 1, and everything else is the set of vectors that map onto 0. And that's what we call the null space. So the rest of R4 maps to 0 and R3. That's the null space, and we have this equality: the dimension of the row space plus the dimension of the null space equals the dimension of our original space, meaning the space we started from, in this case R4. So we have a three-dimensional row space, a one-dimensional null space, mapping to R3. Or we could say rank plus nullity equals n, where n is the dimension of the original space. And that's always going to be the case. Remember that the rank is just the dimension of your row space. Also, the dimension of whatever you map to over here, what actually gets mapped to, the dimension of the range of this mapping, is equal to the dimension of the row space. Because the dimension of the column space is equal to that of the row space.